Good afternoon, everyone. Am I audible?
Yes, ma'am.
Very nice. Okay, thank you. So we'll see for another 1 or 2 minutes. Then I'll start. So still people are joining. So last 1 minute I'll wait. Then I'll start. So you people have a WhatsApp group?
Yes, ma'am.
Okay, can you please add me to that so that if there is any delay or technical glitches, so I can uh, keep in contact with all of you.
Yes, ma'am, I'll do it.
Okay. Okay, so I hope the prime mover slide is visible to all of you. What we discussed in the previous class. Oh, right, very nice. Okay, so in the last class we have just discussed what is a prime mover, what are the different types of prime movers, and we have also discussed about the steam turbine, how they work. Okay, so I'll just revise those things because if anyone absent yesterday, so they can just grasp the things. I'll just run through this and then I will move on to the hydraulic turbines. Okay. So as we discussed yesterday, a prime mover is nothing but a driving force. It is a major device or an equipment which is responsible for the movement. Okay. So if you just talk in terms of this particular course, we can say a prime mover is a device which takes any form of energy as an input and converts that into some useful work or into some mechanical work. Such a device we call it as a prime mover. So we have discussed the advantage, examples for these prime movers as steam engines, wind turbines, or windmills, as you said. And we have gas turbines and also the internal combustion engines, wherein the heat energy which is obtained from the combustion of the fuel is used to run the automobile. Okay, so heat energy is converted into the mechanical energy. So like that, so a prime mover is a device which takes any form of energy at the input and converts that into some useful task that we say as the prime mover. So we have understood what is thermal prime mover and hydraulic prime mover. If the prime mover is using water energy at the inlet to convert that into some mechanical energy, then we say it as a hydraulic prime mover. So you people have understood the nozzle effect, how the pressure and velocity is varied when it passes through the nozzle. And you also understood what are the various parts of a turbine. So these things we discussed in the previous class. Okay. So steam turbine, of course, I had explained you how the pressure and velocity are varying in steam turbine. So just quickly to run through the thing. So it as the name itself is suggesting, steam turbine means it is a turbine which is running with the energy that is obtained from the steam. Okay. So heat energy of the steam is transferred into mechanical energy, which is in the form of the rotary motion. Okay. So the basic principle of operation of steam turbine involves the generation of high pressure steam jet, which is obtained by combustion of fuels and letting that high pressure and high temperature steam to expand in the nozzle to convert the kinetic energy into the mechanical work. Okay. So this high energy steam is passed through the nozzle where the velocity increases and pressure drops, and that will be in turn passed on to the rotor blades, and those blades will set into motion. Okay, that is how the turbine will start rotating. Okay, so these steam turbines are basically used to generate the electric power in thermal power plants. They're also used in ship propellers, pumps, compressors, in textile industries, and industries which are involving machineries. Okay, so they're all we can see these steam turbines, which runs with the help of the steam energy, high heat energy that is obtained from the steam. So in these steam turbines, we have two types. One is the impulse steam turbine, another one is reaction steam turbine. So we discussed this in the previous class. Impulse steam turbine, here we use a nozzle, and that nozzle effect can be seen inside the nozzle, and the pressure and velocity can be controlled. Okay. So we in impulse turbine, the turbine blades are of uniform cross section. So there will not be any pressure variation as the steam glides over the blades. But in case of reaction turbine, we will be having fixed and moving blades arranged in an alternate fashion. So the aerofoil structure of those blades itself will be providing the nozzle effect. So here we won't use a separate nozzle in reaction turbines. Okay. So that is what we discussed in the previous class. Just to show you people how the arrangement is there in both the types of turbines, I have the images here. So before moving on to that, so as I told, in impulse turbine, steam will be expanded from its initial high pressure to a lower pressure before it is delivered onto the moving blades. That is, inside the nozzle, steam will be expanded. Okay. Then it will be directed onto the rotor blades, and the rotor will be set into rotation. Okay, which converts the kinetic energy of the steam into the mechanical energy. So here at the inlet, we will be having a high velocity steam, okay, and that will be gliding over these curved blades, and the output will be the low velocity steam, okay. So this is what is the resultant force, the centrifugal forces that are acting on the blade and which sets the rotor into rotation. Okay, here you can see these are the blades. In this image, you can see these are the blades, and this is the rotor which is carrying all those blades. So here we have a nozzle. The nozzle, the steam, whatever it is coming out of the nozzle, is striking the blades. Okay, and the rotor is rotating because of the force that is acting on the blades, which is obtained from the steam. Okay, so now we had discussed, yeah, this we have used another diagram where I clubbed both. So here we have taken it separately, same diagrams separately. See this, this is the pressure graph and this is the velocity graph. So in case of impulse turbine, as I told, there will not be any change in pressure as the water glides over the blades. So there will be a drop in pressure in the nozzle. So at the inlet of the nozzle, it will be high pressure, low velocity. At the outlet of the nozzle, we will be having high velocity, low pressure. Okay, so that is what the decrease in pressure is indicated with the line AB. When it passes through the blades, there will not be any change in the pressure. So it is indicated as a straight line, horizontal line along BC. Okay. So this is the pressure graph. If you consider the velocity, so through the nozzle, as it passes through the nozzle, velocity increases. So that rise in velocity is indicated from P to Q. Okay. And as it glides over the blades, that velocity is transferred to the blades to set them into motion. So there will be a decrease in velocity. So at the exit, we will be having low velocity. Okay. So this is Q to R, a decrease in the velocity as it glides over the blades. Okay. So the water jet or the steam jet which is coming out of this nozzle is getting deflected by the curvature of these blades, and that will set the blades into motion. So this causes the steam jet to undergo change in direction, which gives rise to change in momentum, and hence the force which will be the centrifugal in nature. So what you have seen in the previous slide. So this is the centrifugal force. There will be a change in direction which will result in change in momentum, which is exerting a force, the centrifugal force on the blades, which sets the blades into rotation. This is what I told you to look into the second law of Newton. Okay, where we say what is the Newton's second law says. I told you people to look into it.
Yes, ma'am. The
Yeah.
rate of change of momentum is directly proportional to the force applied and takes place in the direction of force.
Yes. The rate of change of momentum of an object will be directly proportional to the force acting on it or the force applied. That is what is the Newton's second law says. So these impulse turbines works on the basis of Newton's second law. Okay. So we have a water steam jet that is coming out of this nozzle, which is getting deflected by the curvature of these blades. So there will be a change in direction, so which is resulting in change in momentum, and that will result in a force which is setting the blades into rotation. F is equal to ma. That is what is a well-known equation for Newton's second law. Okay. So now, as you have observed, pressure will change and velocity change, the corresponding values. So whatever I had explained just now, so that is written here. So you can just go through these things when you get prepared for the exams. Okay, so these impulse turbines are also called as D-level turbines. These are named after the scientist. D-level turbine, Parsons turbine. So they are named after the uh, founder. Okay, the Gustav D-level. So he developed this single stage impulse turbine. So that is why it is also called as D-level turbine. Okay, so don't get confused by the terminologies used. Impulse turbines are nothing but D-level turbines. So next we have reaction turbines. As I mentioned here, we won't use any nozzle as such, but the alternate arrangement of fixed and moving blades itself provides the nozzle effect to the steam that is flowing through the turbine. Okay. So as you can see here, so we have fixed blades, moving blades, fixed blades. This arrangement will be there. Okay. So this arrangement and the aerofoil structure of the blades itself will provide the nozzle effect. Okay, so as you can see here, uh, the fixed blades acts as nozzle region. So there is a drop in pressure, and moving blades again drop in pressure. So here this continuous arrangement, alternate arrangement of these things is providing the nozzle effect. Okay, so you can see there is a drop in pressure in all the stages. Okay. So we can't say, as we saw in impulse turbine, the pressure remains constant as it glides over the blades. But here it is not. Okay. So velocity also in the fixed blade region it increases. In the moving blade region it decreases because that energy is getting transferred to the blades to set them into motion. Okay. Again it is increasing and decreasing. So this is how the pressure and velocity varies in the reaction steam turbines. Okay. See, here you can see the arrangement of blades. So multiple stages we will be having, fixed and moving blades. The high pressure steam passing in the first row of fixed blades undergoes a small drop in pressure, causing the increase in velocity of the steam. The drop in pressure energy is resulted in increase in the velocity. So then it enters into the first row of moving blades. Okay, from the fixed blades, it is entering into the moving blades. So there it suffers a further drop in the pressure, and the velocity energy is converted into the mechanical energy of the rotation of the rotor because it is the moving blades region. Okay. So in fixed blade, there will be a pressure drop which is gained into the velocity. When it glides over the moving blades, there is further pressure drop and the velocity will be transferred to the moving blades to set them into motion. So the velocity also decreases in that moving blade region. Okay. So that simultaneous occurrence will be there, the repetitive occurrence based on how many say number of such rows we are using the fixed and moving blades arrangements. Okay. So people are following.
Yes, ma'am.
Yes, ma'am.
Very nice. Very nice. So this is just a revision what I had covered in the last class. Okay. So in case of impulse steam turbine, so we are using nozzle. So steam is completely expanding in the nozzle before it enters the moving blades. So here, in case of reaction turbine, steam is completely expanding in the successive arrangement of these fixed and moving blades. Means in the blade region only it is getting expanded. No, there is no nozzle. So here in case of impulse steam turbine, turbine blades have symmetrical profile. So I told you they will be having uniform cross section, but here they will be having aerofoil structure. So don't go by this diagram and ask me that there is no aerofoil structure. Okay, so it is bit not up to the mark. Okay, so this diagram. Okay, so actually it is supposed to be an aerofoil structure. I think I had shown you in the previous class. Structure should be. Sorry, let me just try one more time. This is the top curve and this will be the bottom curve. So this should be the aerofoil structure. Okay. The other one in case of impulse, this will be the top curve and this will be the bottom curve. There is no variation in cross section. Okay. So when listing, the turbine blades have symmetrical profile, whereas they will be having aerofoil profile. So pressure on both the ends of the moving blades is same in case of impulse turbine because there is no change in pressure as the steam glides over the blades. Okay. So in this graph, we had seen that there is no change in pressure. This B to C is a straight line. Okay. So there is no change in pressure. Whereas in case of reaction turbines, we have the drop in pressure in all the stages. Okay. So the pressure on two ends of the moving blades are different. Since there is a large drop in pressure in the nozzle, the steam speed as well as the rotor speed are high. So the pressure energy is getting converted into velocity, so that can be transferred onto the rotor blade. So the maximum speed we can expect here. There is smaller pressure drop, so the speed and of the rotors will be relatively low. Okay. Because of larger pressure drop in the nozzle and less number of stages, size of the impulse turbine for the same power output is small. The size is small. Here it is. There are number of stages. Okay, as I told, there are alternate arrangements of fixed and moving blades. So the stages are more. So the size is big. Of course, the next difference goes with the previous one. It occupies less space and it requires more space. So this is suitable for small power generation and this is for medium and high power generation. So due to high rotor speed, the compounding is required. What does it mean is, so all the pressure energy is getting converted into velocity. So the rotor which is getting into motion, it will be rotating with very high speed. But I cannot just couple that output directly to some motor because my requirement may be different. Suppose at the output, if the rotor is rotating at say for example 10,000 RPM, but I want to do some work which is requiring only 100 RPM. Okay, so that is why we need to have compounding done. Compounding means you can reduce the speed to the required level. Okay, so because of the high rotor speed, we have to go for compounding to monitor the or to control or to modify the speed of the rotor at the exit. Okay, so here it is not required in case of reaction turbines. Okay, so examples are D-level turbine and here Parsons turbine. So when it comes to the hydraulic turbines, we have in Pelton and Francis and Kaplan. Okay, so I'll just come to that. I hope it is clear up to this. Yes?
Clear, ma'am.
Okay, fine. So what is that the gist of whatever I had explained so far is what you need to know is you should know what is a prime mover. You should know what are the types of prime movers and what is a steam turbine, the types of steam turbines, and what happens in impulse and what happens in reaction. Okay, if you know these things, it is sufficient. Okay. So at the end of this slide, you must be aware of these concepts. Clear? So moving on to the next, we have hydraulic turbines. Very similar to the steam turbines. Here we will be using the water energy as at the inlet, and that will be setting the rotor into motion. Okay. So hydraulic machine that converts the hydraulic energy into mechanical energy, that is called as turbine. Okay. If I go reverse, in the reverse order, if I say that the mechanical energy is getting converted into hydraulic energy, I can say it as a pump. So can anyone give me example for this? Device which converts mechanical energy into hydraulic energy. Where you can see this? Simple, your day-to-day life example it is. And of course,
Ma'am, tap.
Ma'am, water tap.
okay, so not exactly the tap, the pump which is used to lift the water from the sump to the overhead. Okay, so you can say that, which is converting the mechanical energy into the hydraulic energy. Okay, so basically this turbine is a, rotating device. It is a rotary device. Okay, this turbine, in case of these hydraulic turbines, so it is gaining the energy from the water and using that water energy, it is going to be set into motion. So this is a simple example of a power plant. So what happens in a power plant and how the construction will be, where the turbines are used. So this is the region where the turbines are mounted. So you are going to study three different turbines, that is Pelton, Francis and Kaplan. So this is the region where the turbines are actually mounted in a power plant. So it is an example of hydropower plant. So we have a reservoir here and dam constructed for that purpose. So water which is coming out of this reservoir is striking the turbine blades. So the turbine is setting into motion. So it will be rotating. So whatever the energy that is generated here, that will be stored in a generator. Then it will be transferred into transformer in the powerhouse. Then it will be sent to the destination through power lines. Okay, this is the outer construction of an hydropower plant, and these are the turbines which are under consideration in this particular chapter. Okay, so from the reservoir to the turbine, we use a mechanism or an element to carry the water. So such large pipes which are giving the connectivity between the reservoir and the turbine, so they are called as penstock. Okay, the large pipes which are giving the connectivity between the reservoir and the turbine are called as penstock. Okay, so how these turbines are functioning? What are the different types of water turbines? That we are going to see in the next slide. As you can see in this, based on at what height I am mounting this turbine, means what I mean to say is at what height we have stored the water, and based on that we are going to use different turbines. Okay, and how the water is entering into the turbine. Based on that, we are going to have a classification. Okay, what is the speed at which the turbine is running? That also going to decide the type of turbine. Okay, so based on this, we're going to try to classify the turbines, water turbines, into different categories. So according to the type of energy at the inlet, we have impulse turbine and reaction turbine. So whether there is kinetic energy or both kinetic and pressure energy are involved at the inlet. So depending upon that, we have impulse turbine and reaction turbine. If there is only the kinetic energy of the water which is getting converted to mechanical energy, and it is called as impulse turbine, and Pelton wheel is an example for that type of turbine. If there are both pressure energy and kinetic energy are involved at the inlet, then we say it as a reaction turbine. So Kaplan and Francis are the examples for that. So this is most frequently asked question. Write the classification of hydraulic turbines with the examples. So then you have to write all the three categories. So all these three categories along with the examples. Kaplan comes where, Francis comes where, Pelton comes where. So all that examples also you have to quote. This complete slide you have to understand properly. So based on the type of energy at the inlet, we have impulse and reaction turbine. Based on the direction of flow of water, we have tangential flow, radial flow, axial flow, and mixed flow, which means how the water is entering into the turbine. If I say this is the turbine, okay, if the water is entering like this, so it is tangent to the turbine. So it is tangential flow. Okay. So next is radial flow. If this is the turbine and water is entering radially inward from all the directions, then I say it as a radial flow. Means how the water is entering into the turbine in the rotor casing. Okay. So this is radial flow. Okay. If I say axial flow, suppose I'll take the turbine here. Okay, and the water is flowing in this direction along the shaft and it is striking the blades here. So this will be axial flow. This is the shaft and the water is entering from all the sides like this and it is falling onto the blades. Okay, and it will be moving out like this. So this we say it as axial flow. Okay, then mixed flow entering radially and leaving axially. So there will be a draft tube attached here and that will be taken, water will be taken out through that draft tube. It is entering radially but leaving axially. So then we say it as a mixed flow. So according to the direction of flow of water, we have these four classifications: tangential, radial, axial, and mixed flow. Is that clear?
Yes, ma'am.
Okay, fine. So next is based on the availability of water. At what height? Head in the sense the storage height. Okay. So at what height I have stored the water in the reservoir. Based on that, we have high head, medium head, and low head. So these values are not fixed. Okay, they are sometimes it may be this value in India, it may be different in US. So it is not fixed value. Okay, so it keeps on varying. If it is stored at very high height, then I say it as a high head turbine and Pelton wheel is an example. If it is stored at medium height, then it is medium head, then we say it as Francis turbine. Low head means it is Kaplan turbine and the head height goes less than 50 meters. Okay. So in this tangential flow means Pelton, you have already studied this. Radial flow, Francis turbine. Axial flow, Kaplan. Mixed flow means modern Francis turbine, and this is the one which is more frequently used or more um, uh, which is in use actually in many of the turbines or in many of the applications. Okay. So this is the detailed classification of hydraulic turbines. So if you just observe in all the category, we have only the three turbines quoted as examples. One is Pelton, Francis, Kaplan. Pelton, Kaplan and Francis. Pelton, Francis, Kaplan. So these are the three hydraulic turbines which you are going to study in detail. As I already mentioned, impulse turbines are also called as D-level turbines. Here, potential energy will be getting converted to the kinetic energy by the nozzle and jet of water is directed onto the turbine's blades, which will reverse the flow. Okay. This resulting impulse will spin the turbine and leaves the fluid flow with diminished kinetic energy. So after striking the blades, the kinetic energy drops because it gets utilized to run the blades. So Newton's second law describes the transfer of energy in impulse turbines that we have already seen. The very important point is there is no pressure change as it glides over the blades. So Pelton wheel is an example. Of course, you have already, sir has already explained this. I'll just straight away go to the diagram. Have you seen this video in that class?
Yes, ma'am.
Okay, fine. So here what happens in case of, I'll just say few points, the gist of it. So it is a tangential flow, high head water turbine. So whenever you take any type of turbine, let it be a Pelton, Kaplan or Francis, the very first sentence is you should state that what type of turbine it is when writing the answers. So Pelton means it is a impulse tangential flow high head water turbine. Okay. So if I just go to the classification, you can see Pelton is impulse. According to first classification, it is impulse. Next classification, it is tangential flow. Next classification, it is high head. So Pelton turbine is an impulse tangential flow high head water turbine. Okay. If I say Kaplan, it is reaction axial flow low head water turbine, like that. So very first statement should be what type of turbine it is. You should state the type of turbine while writing the answers. So it is a tangential flow turbine. So we use penstocks to carry the water from reservoir to the turbine. So we have this spear-headed nozzle which controls the flow of the water. Okay. And water which is coming out of this nozzle is striking these bucket-shaped blades and it is setting the rotor into rotation. Okay. And water after striking this bucket, it will be falling into the tail rails, which we use for water collection. Okay. So the number of blades is also a very important parameter when we design this Pelton wheel. If there are more number of blades, that is also a problem. If there are less number of blades, that is also a problem. More number of blades means all the blades may not get the impingement. Less number of blades means the water may be wasted. Okay. So before the next blade comes in position, the water may fall into the tail race. So optimum number, deciding the optimum number of blades is another very important parameter in case of these Pelton wheels. Okay. So here the velocity at the inlet will be greater than the velocity of the water at the outlet because so as it comes out of the nozzle, it will be at very high velocity and as it glides over the blades, there will be drop in the velocity. Okay. So whatever the power developed here, this will be equal to the product of the impulsive force and the velocity of the bucket. Okay. If the velocity of the bucket is 0, then there is no power developed because there will not be any impulsive force. If there is no impulsive force means bucket will not set into motion, so the power generation will be 0. So any one of it goes 0 means the power will be 0. Okay. So we will get the maximum power when the pressure is maximum. Power will be maximum when this velocity will be half of the jet velocity. When the bucket velocity will be half of the jet velocity, then we get the maximum power output. Okay. So stationary buckets means bucket velocity will be 0. So the power generation will also go 0. So this is another important thing that you are supposed to know. Okay. So I'm not going to say how the water flows and all. So just can refer to that as it is already done. So reaction turbines, pressure changes as it moves over the blades. Okay, that is what is happening in reaction turbine, as we won't use any nozzle. So here we can say there is these reaction turbines works on the principle of Newton's third law. Okay. Examples are Francis and Kaplan turbine. So this is the Francis turbine. Okay. So is that clear up to this? The classification as well as the construction of Pelton wave turbine. Is that clear?
Yes, ma'am.
Yes, ma'am.
Okay, fine. Thank you. Yeah. Any doubt?
No, ma'am.
No. Okay, fine. So now we understood the detailed classification of hydraulic turbines, and we also understood the Pelton wave turbine. Okay, so I'm not going to that particular video. Of course, you can find it in YouTube also. If you just search comparison between Pelton, Kaplan, and Francis, the very first video you will get that one only. Okay, you can watch there also. So next, here we have Francis turbine. So what type of turbine it is? Can anyone classify this?
Yes, ma'am. This reaction, axial flow and medium head turbine.
Come again? Sorry.
It's a reaction, axial flow in the and the medium head.
Pavan. Yeah, Pavan. Two parameters are correct. Two classifications are correct. Why in one you went wrong? So anyone else?
Is it radial?
Ma'am, it is radial flow turbine.
Yes. So Francis turbine is a reaction turbine wherein we can see the radial flow and medium head.
Can we say it mixed flow turbine?
Sorry. Yeah, modern Francis, if you go, yeah, modern Francis, if you go, you can say it as a mixed flow also. Okay. So since it is a reaction turbine, as I mentioned in the previous class, unlike the impulse turbines, reaction turbines requires a pressure casement. Okay, they require a pressure casement. So this spiral casing, we say this is the containment. Okay, the outer body, what you can say, this spiral casing, we say it as. So this is the casement, the pressure casement. Okay. So here water is entering from here, and we will be having the two set of blades, as you all know. One is the fixed blade, another one is moving blade. So here what we say them as these guide blades and runner blades. We say them as guide blades and runner blades. So water is entering through this spiral casing and it just gets guided by these guide blades and it will enter into the rotor and it will strike on these runner blades or the rotor blades. Okay. Then it will impinge on those blades and sets the rotor into motion and that will be collected through the draft tube into the tail race. Okay. Whereas in case of Pelton, we won't require any such draft tube for collection of water. It will be directly let into the tail race. But here we need a draft tube because we have enclosed everything with this casing. Okay, so here we need a separate arrangement like draft tubes for collecting the water from the inside part of the turbine to the tail race. Okay. So this is the draft tube which is used to take the water out of the turbine. Okay. So how these blades are guiding it and how the water is striking, that we will see here in the next slide. So it is a medium head. Okay. Inward flow, radial flow, both are same. Reaction turbine. Okay. It consists of a spiral casing, as I said. So which will be enclosing the number of stationary blades and moving blades. Vanes are nothing but blades only. Don't get confused by the terminologies. Different terminologies what they use. So water at high pressure enters through the inlet and it flows radially inwards through the guide blades, taking the help of the guide blades. Then it moves on to the runner blades. Okay. So the angle of these guide blades can be adjusted by using a lever, and you can control the flow of the water. Okay. Yeah, here we use a draft tube, and then water will be discharged into the tail race through the draft tube. So whatever I explained, those are put in words here. See, these yellow colored one are the guide blades, the angle of which can be adjusted. And this is the runner blade. Yeah, here these are the guide blades and this is the runner blade. And water will be entering from here, gets guided by these guide blades and it will enter and strikes the runner blades. Okay. Let me just check whether it works or not.
Francis turbines are the most preferred hydraulic turbines. It contributes.
Is it audible?
Yes,
Yes, ma'am.
Oh,
Yes, ma'am.
yeah.
Francis turbines are the most preferred hydraulic turbines. It contributes about 60% of the global hydropower capacity, mainly because it can work efficiently under a wide range of operating conditions. Most important part of Francis turbine is its runner. It is fitted with a collection of complex shaped blades. In runner, water is entered radially and leaves axially. During the course of flow, water glides over runner blades. Francis turbine blades are specially shaped. You can note that blades are having thin airfoil cross section. So when water flows over it, a low pressure will be produced on one side and high pressure on the other side. This will result in a lift force. You can also note one more peculiar thing about the blade. It is having a bucket kind of shape towards the outlet. So water will hit and produce an impulse force before leaving the runner. Both impulse force and lift force will make the runner rotate. So Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. Thus, as water flows over runner blades, both its kinetic and pressure energy will come down. Since flow is entering radially and leaves axially, they are also called mixed flow turbine. Runner is connected to generator via a shaft for electricity production. This arrangement is fitted inside a spiral casing. Flow is entered via an inlet nozzle. Flow rate of water will get reduced along length of casing, since water is drawn into the runner. But decreasing area of spiral casing will make sure that flow is entered to runner region almost at a uniform velocity. Stay vanes and guide vanes are fitted at entrance of runner. The basic purpose of them is to convert one part of pressure energy to kinetic energy. Flow which is coming from the casing meets stay vanes, they are fixed. Stay vanes steers the flow towards the runner section, thus it reduces swirl of inlet flow. Demand for power may vary over time. The guide vane mechanism is used to control water flow rate and make sure that power production is synchronized with power demand. Apart from controlling flow rate, guide vanes also control flow angle to inlet portion of runner blade. Thus, guide vanes make sure that inlet flow angle is at optimum angle of attack for maximum power extraction from fluid. Low pressure at exit side of turbine may cause serious problems of cavitation. So a carefully designed draft tube is fitted at exit side to discharge the fluid out. Draft tube will transform velocity head to static head due to its increasing area and will reduce effect of cavitation. Hope you had a nice session on working of Francis turbines. Thank you.
I hope it was clear.
Yes, ma'am.
Okay,
Ma'am.
fine. Yeah, so here also you can see in this simple animation how the rotor blades on the rotor are rotating and outer are the guide blades. So that was regarding the Francis turbine. So whereas in case of Kaplan, again it is also a reaction turbine, which is with the low head, and here we say that it is an axial flow turbine. Okay. So Kaplan is an axial flow turbine, as I just showed in the previous slide with the sketches. So shaft will be like this. We will be having a hub, rotor hub. So it will be carrying blades on it like this. So water will be coming and striking these blades. Okay. This is the axis. So since it is flowing, water is flowing axially, so we say it as axial flow. Okay. So Kaplan turbine is an example for axial flow turbine. Okay. So here this hub will be carrying not more blades as we saw in case of Impulse and Francis turbine. So it will be having very less number of blades, like 4 to 6 blades will be there on the hub. Hence it is resembling a propeller of a ship. Okay. This is one common quiz question. Name the turbine which resembles the propeller of a ship. So that is what is Kaplan turbine. Its design is so that it resembles the propeller of a ship. See, other working principle, everything remains the same. Only the entry and its construction are different. Here also we use L-shaped draft tube to discharge the water into the tail race. Yes. So as you can see here, same diagram holds good for both Francis and Kaplan. Only changes these internal blades. Okay. So there we had different blade structure. So here the blades are different. This is what is the region which is resembling the propeller of the ship. Okay. So this, if you just observe in this 3D, you can just understand. This is the generator, what you have seen, and we have a shaft which is connecting the generator and the turbine. And we have these guide blades, and water is entering from here and it is striking these blades. So this is called as hub, which is carrying the blades. Okay. So number of blades varies from 4 to 6. So shaft axis is this. That is why it is called as axial flow. So water is entering like this and it is striking the blades axis. That is why it is axial flow. Okay. So rest of the principle remains the same. You can see here the actual plant picture. If you get a chance, you can always visit any of the power plants and you just see what type of turbines are installed there. This is another one, the other view. Okay. This is the one which is there in our lab, but unfortunately we are online, so I couldn't take you people to the lab. So all these turbines, we could have seen the working of it in the lab session, but which is not possible now. Let's see, once the offline classes resumes, we will visit. We will just see this.
Kaplan turbines are suitable for power extraction when water energy is available at low head and high flow rate, which means they are suitable for operation when water is stored in a big reservoir at a relatively shallow altitude. In Kaplan turbine, flow is entered through a spiral casing. Decreasing area of casing makes sure that flow is entered to the central portion almost at uniform velocity throughout the perimeter. Water after crossing the guide vanes passes over the runner. Finally, it leaves through a draft tube. Most important part of Kaplan turbine is its runner. Cross-section of runner blade will have a curved shape. When water flows over it, it will induce a lift force due to airfoil effect. Tangential component of lift force will make the runner rotate. This rotation is transferred to a generator for electricity production. Kaplan turbines are axial flow machines, where absolute velocity of flow is parallel to axis of turbine. Water is precisely made to pass through rudder blades with help of a shroud. Power demand may fluctuate over time. A governing mechanism, which controls position of guide vanes, is used to control water flow rate. This can be for varying power demand. Blades of Kaplan turbine are designed to operate under a wide range of operating conditions. A rotating blade experiences relative velocity of flow. The fundamental thing in blade design is relative velocity of fluid flow should be at optimal angle of attack in all cross sections. Even though absolute velocity is axial, relative velocity will be inclined depending upon blade velocity. Inclination of relative velocity increases as we move from root to tip due to increasing blade velocity. There should be continuous twist in blade from root to tip so that at every cross section the angle of attack is optimum. With varying flow condition, relative velocity will change drastically. Kaplan turbine blades are adjustable. When flow rate is high, relative velocity of flow will be more axial, so blade should pitch vertically. If flow rate is low, relative velocity of flow is more tangential, so blades are pitched in tangential direction. In short, pitching action of blade makes sure that blade is still an optimal angle of attack, even under varying flow. Apart from controlling the flow rate, guide vanes have got one more function. They help in controlling swirl of flow. If guide vanes were not present, the flow would be highly swirling in nature due to its tangential entry. Such a flow would reduce performance of turbine drastically due to its poor angle of attack. So guide vanes control swirl of flow for optimal angle of attack. The biggest challenge in design of Kaplan turbine is how to overcome problem of cavitation, which causes material erosion and vibration. Cavitation is unavoidable in Kaplan turbine, since in most of the regions, pressure goes very low. But damage due to cavitation can be reduced by using suitable blade material and use of anti-cavitation fin. Draft tube, which transforms dynamic pressure to static pressure due to its increasing area, also helps in reducing cavitation effect. Thank you. Hope you got a good understanding on Kaplan turbines.
Okay, so was it clear?
Yes, ma'am.
Okay, so in these reaction turbines, those angle of attack and flow control are the two things which needs to be monitored in a very high way, because the swirling effect may decrease the efficiency of the turbine. Okay, so that is why we need the proper setting of angle of those blades so that the swirling can be avoided. Okay. And cavitation is the another point what you need to observe in the turbines. Okay. So a proper pressure casement is required and proper flow control should be there so that we can avoid those cavitation and the swirling effects to increase the performance of the turbines. So this is about the hydraulic turbines which are there for your syllabus. Next class I will talk about the gas turbines. We'll see how the gas turbines works and how they are classified and all that in detail in the next class. Okay. The comparison video is also there. You can just go through it. Activity, I think we can have it in the next class. Okay. The next class, I will just run through all these things, whatever I covered just now, and then we will take up the activity and further we will continue with the gas turbines. Hope it is clear for all of you. Any doubt? Yes? Anyone having any doubt?
No, ma'am.
No. Okay, so let me take the attendance quickly. You answer for both yesterday and today. Pavan,
Present, ma'am.
yesterday also you are there?
Yes, ma'am. Yesterday also I was there.
Okay, fine. So next is just a second. Give me a second. Okay, Nidhi,
Ma'am.
you are there in both the classes, right?